Okay, it's already started recording. So people who are late, they can just watch the earlier bit of the recording. I can go through the little bit of theory first, or do you want me to just jump straight into the questions? Well, a few other people have just joined us. I tell you what, guys, I'll probably start off with a little bit of theory first, okay? So let me just, let me see, where is it? Let me just kick you off, early in the morning, you are still, a bit sleepy, I guess. Let me just kick you off with a little bit of theory about chemical energetics. Now, the biggest problem that students have in this topic is they don't understand what is called system and what is called surrounding. So system is essentially the chemical reactions itself, the particles itself. So that is the chemical reaction. When you write an equation, that is the system itself. It's basically the reactants going to the products. Basically things which you cannot see with your eye because they are the particles. So what happened to the particle? So there are things which you cannot see with your eye. And what you could observe would be the effect on the surrounding. And this is the relationship between system and surrounding. This is observable. So this is the macroscopic, macro meaning the big stuff. So things you can see on the outside, observable, measurable. So you can quantify it. So typically, usually these are the solution, because when we do our chemistry, we do them in solution form, meaning to say we do them dissolved in water. So there is the aqueous solution format. So in the context of O-level, you have this thing where you have an exothermic reaction. And you know that in an exothermic reaction, the enthalpy change is lesser than 0. It's negative. So in an energy profile diagram, you have energy on the y-axis, and then you have progress of reactions, or you have extent of reactions. So which one will have higher energy, the reactant or the products? Let me ask you, Yasmin. There, Yasmin? Hello.
Yes, sir.
So Yasmin, which one will have higher energy? Is it the reactants or the products for an exothermic reaction?
Exothermic would be the...
So if I draw in a reactor,
the
reactants will have higher energy because the reactant will have lost the energy. You see, it's an exothermic. Exo means it gives out, it loses the energy. So from the reactant to the product, that is your arrow, that is going down, that is why it's negative. Now, the biggest mistake a lot of students make is they put a double-headed arrow. Is that the Shakira who is unwell, or is this the Shakira who is okay today? So I'm just gonna mute you, yeah, okay, because yeah, okay. Anyway, yeah, just continuing on where I left off. This reactant has high energy than the product because the reactant loses energy to the surrounding. This is system. System is the reactant going to the products. And when you complete the energy profile diagram, they're gonna look like that. There's actually a really terrible energy profile diagram. So your words shouldn't overlap. Your activation energy is from the start, basically from the reactant to the top of the peak. Again, avoid the double-headed arrow. Direction matters in this topic from the start to the end. What we have then is what will happen to the surrounding. So on the left-hand side, I have drawn what happened to the system, but then that is what we see on the system. This is what you do in practical, and you will have your practical exam based on what was announced at the press conference yesterday. If you are okay and stuff, you will definitely have a practical exam, and it is something that you need to think about what you have done. You put the thermometer, you have a plastic cup or a styrofoam cup inside a beaker, and then you have a solution in there. You have a thermometer in there. So you record, you need a stopwatch as well, because you need the time. You see the x-axis, you need to record the time, and the thermometer, which will record the initial and the final temperature as the reaction progresses. So you put the thermometer in there initially for like the first 2 or 3 minutes. so that the temperature will actually be for the solution and not for the surrounding air, so that the temperature will equilibrate and get to a constant which you will record as the initial temperature. Now, at this particular time, when you add in a solid, so this could be an acid and then you add in metal or add in metal carbonate, then this is the time when you add it. You do not record the temperature. Usually you record it the next minute after. And then suddenly it will go all the way up there, and then it might go up and then further down like that. And then you are asked to draw connect the dots. So one line, and then you have to extrapolate. Extrapolate means you have to extend the line a little bit. Okay. So what happened then is you draw your best fit straight line like that. Okay. And then this is the time when you started adding in the solid. There is no temperature recorded when you added in the solid, because that was when the reaction happens. It gives you the highest temperature rise. The highest temperature rise was quite sudden that you couldn't measure it. That is why you have to do an experimental method. And now you have to do a graphical method to get this maximum temperature. So what happened then is you would have extrapolated your graph. And this point where they meet, that is called the highest temperature or the final temperature. And this is what you need in your practical study as part of your calorimetry. So delta T, change in temperature, is final temperature minus initial temperature. Your temperature of the solution goes up because the reactant loses heat energy to the surrounding. That's why your product have lesser energy than the reactant, because that energy has gone to the surrounding system, surrounding. Okay, in this kind of experiments, you want to prevent heat loss, so you will cover with plastic lid. What else can you do? You can insulate the inside with some cotton wool. So you can put some insulating cotton. So these are like insulating cotton wool. Anything that can prevent heat loss will make the experiment more accurate. You can use a plastic lid. Anything that can prevent heat loss will make the experiment more accurate like that. Of course, it will cool down later on because, you know, just like your hot water, it will cool down back to room temperature after some time because, you know, that energy will get exchanged with the energy of the air molecule eventually. Okay, that is basically in a nutshell what happened in the exothermic reaction. Now I'm ready to move on to the endothermic reaction. So like I said earlier, I will spend like a few minutes to go through the underlying theory first. And this is energy. This is progress of reaction. And then your reactants would have absorbed energy from the surrounding. So your products will have more energy than your reactants because this is endothermic. Endothermic means your system absorbs heat energy from the surrounding. The delta H is greater than 0. Direction matters. Avoid double-headed arrow. Do not draw double-headed arrow. Single direction from the start to the end. Reactant to the product, that is enthalpy change, is going up. That's why it's positive. Activation energy from the start to the top of the peak. This is called activation energy. Again, it's going up. It has a positive sign. You must have a sign in this topic because it's to do with enthalpy changes, which has direction and therefore sign, value, and unit. This one is a experimental thing. This is what happened with the surroundings. So with your surroundings, you're going to see the opposite kind of effect. And this can happen in practical as well. So what happened is you would have a temperature like that again. And then because this is endothermic reaction, it takes in heat energy from the surrounding. So the surrounding will get colder. What you see is the temperature will drop all the way down. And then it will warm back up again because, you know, it will equilibrate back to room temperature eventually. So what you do in this kind of thing is, well, again, draw a line like that and then draw a line like that. Okay, my graph is not that great because, yeah, I didn't extend it that much, but you will know better in practical studies that you're expected to draw some graph. And then this is the point where you added in the solid. The time when you added in the solid or when the reaction started, there was the time when you don't record the temperature at all. And that will be your lowest temperature. So this is the final, and that is your initial. So again, not just your final or initial, but that is your delta T, which is final minus initial temperature. This is a decrease in temperature because the reactants absorb the heat energy to form the product. The product have higher energy than the reactants, which is why you see the opposite happening to the surrounding, because this takes in the energy. This energy is taken from the surrounding get colder. It's the same kind of setup as this experiment, but of course, this is to do with heat being absorbed, regardless heat being absorbed or heat being released, as in exothermic reactions, or heat being absorbed for endothermic reaction. Your objective is prevent heat loss or essentially prevent heat loss. You want to ensure that all the heat generated, released, or being absorbed by the solution, by the system, matches whatever the surrounding will see, and therefore this kind of insulating purposes or insulating adjustment, like using a plastic lid or insulating cotton or some other improvement you can think of that can improve the accuracy of your experiment. Now, moving on to the next big chunk of this topic, which is not really your O-level, is basically this list of definitions. So the most important definition in AS include this formation. So that is your standard sign. So this is called standard enthalpy change of formation. So the F there refers to formations. We got to think about the standard conditions. A lot of students, they memorize these things, without thinking about the meaning, and that is where you have made a huge mistake. You have not associated any meaning to definitions, and that is the first mistake you have made, learning things the difficult way. Now, enthalpy change of formations is best done by, thinking about the definition. So this is enthalpy change when you do what? When 1 mole of a substance. So you have 1 mole of a substance because of the definition, kilojoule per mole. And you have this in the data booklet. This is per 1 mole. The question is per 1 mole of what? So in the formation context, 1 mole of a substance is formed, okay? And this is from its elements. And then these elements must be in their standard state. So my definition might be different, or slightly different from yours, slightly different from textbooks, slightly different from marking scheme. But as I told you from ionization energy definition previously, it's all about getting all the contents correct. So I like to remember definitions by trying to break them down into important point. You don't get any point there, you get your point there, and the final one, which is under standard conditions. And I always make it a point of writing out the standard conditions, because we never know when the question is going to ask you what is or what are the standard conditions, especially also in A2 definition. So make sure you know this thing. There is something very important that I want to show you. This is actually I'm going to do the combustion first, and then we're going to do the other one. So this is the standard again, and then the C there refers to combustion. And then this is, again, kilojoule per mole. The question is per mole of what? Per mole of what? So this is combustion. So do not get confused between the combustion and the formation. So combustion is when 1 mole of a substance is burned completely in excess oxygen. So when you combust something, and this one has to be complete combustion, and therefore you must have excess oxygen. If you don't have excess oxygen, you're not going to be burned completely. We don't know about the products because you can have different substances combusting, and then this must be in their standard state. So 1 mole of a substance in standard state. Well, actually not just the substance, but everything, all or everything in standard state under standard conditions. But again, you will see that my definition might be slightly different, slightly variable compared to what you would have seen in textbooks or in marking scheme or whatever definitions you have done previously in your entire life. That is because definitions can change slightly, but you must have all the important context where I talk about the 1 mole, where I talk about what is happening to that 1 mole and the excess oxygen. The standard conditions are typically what are additional point to that definition alone. The very last definition that you would have learned in AS chemistry and required would be the bond energy. But this bond energy refers to the covalent bond. Again, it is kilojoule per mole in the data booklet. Now, this is per mole of what? This is per mole of covalent bond. So here, it's not 1 mole of a substance, it's 1 mole of a covalent bond. This bond energy is always endothermic because, well, when I say endothermic, it's based on the definition. It's the energy needed or energy required to break. to break 1 mole of a covalent bond. So that covalent bond, okay, is broken down into gaseous atoms, okay, into atoms. Probably I can skip the gaseous bit first because of what I'm going to say in the next step. Everything must be in the gaseous state. Everything in the gaseous state. So the left side and the right side must be in the gaseous state. This is the one thing which is very important. Everything must be in the gaseous state because people are asked to write questions, especially when you come across Born-Haber cycle in A2 chemistry. If you don't have it in the gaseous state, you run into problems later on when you try to compare with enthalpy change of atomization, and that is A2 kind of energetics. I'm ready to write a couple of questions. So there are some identities. These identities are very important. When you think about the formation of element, you are forming 1 mole of the substance, which is the element. From its elements, under standard state, in standard condition, is always going to be 0. Okay. Combustion of oxygen, you are burning 1 mole of oxygen in excess oxygen. Oxygen does not burn. Oxygen supports combustion. Oxygen relights glowing spleen, but oxygen itself is not flammable. Be very careful, okay? So this thing is going to be 0 because you think about the definition, oxygen burns in oxygen, doesn't make any sense at all. The next thing, there are 2 more identities that you need to keep your eye out for. You write equation and then you can see. If I write the equations, the formation of water, So when I write formation equation, I write 1 mole of the substance first, formed from its element. The element is diatomic element, even O level and IGCSE student know that. So 1 mole of the substance means I cannot change the one in front. I have 2 hydrogen atoms, 2 hydrogen atoms. I have 1 oxygen atom, but I cannot change the identity here, only 1. I cannot change the identity of the element, and therefore I must have a half there. This is the idea of enthalpy change of formation. You form 1 mole of the substance, and you have to keep your eye out for that. Everything in their standard state. So this is the formation of H2O. I am now going to write another equation, which is going to be the combustion of hydrogen gas. So this is now combusting 1 mole of the substance, combust 1 mole of the substance. Hydrogen burns in oxygen with a pop sound, and then you produce water, which extinguishes the flame. I must have 1 mole there, and therefore in doing so, if I only have 1 mole of the substance, I have 2 hydrogen atoms. I cannot change the number here anymore because of 1 mole of H2. Not because of that, but because of these, because of the definition. Follow the definition and you will be fine. And therefore, this has to be half mole of O2. This is gas, and liquid. And what you could see immediately is the 2 equations are the same. The 2 equations are the same, and therefore your identity, this is point number 3 that I want to make. The formation of H2O is equal to the combustion of H2. Why? You write the equation for one, you write the equation for the other one. They are exactly the same equation, exactly the same multiple, and therefore this must be equal to that. Okay, these are popular things that you need to keep your eye out for. The last thing is going to be the formation of CO2. So this is carbon dioxide being formed from the element, carbon and oxygen, solid gas and gas there. So that is forming 1 mole of the substance. Follow the definition. Forming 1 mole of the substance from its elements in their standard state under standard condition. The next one is going to be combustion of carbon. You will see that burning 1 mole of the substance in excess oxygen, everything in their standard state under standard condition, and you will get the exact same question, and which is why the combustion of carbon is the same as the formation of carbon dioxide. And this is identity. Identities are not to be memorized like sine squared theta plus cos squared theta equal to 1. Identities in chemistry are to be remembered by writing out equations based on the definition. The water and the CO2 are extremely important because of their formation, because of forming this thing as a product when you get complete combustion. And that is why it's important that you know where things are going. Last but not least is to do with Hesse's law or Hesse cycle. Hesse law is basically conservation of energy in a nutshell, but instead of conservation of energy, we say it's to do with enthalpy change. Enthalpy change is in kilojoule per mole. Energy is in kilojoule or joule. Energy is not enthalpy change. Enthalpy change is to do with how many mole is involved. So this is enthalpy change of a reaction. Does not depend on which path you take, but then what is very important is that it is independent, or you can say not dependent. Okay, a lot of you will have slightly different definition of this, which is perfectly fine. But whatever you do, you must be able to, apply the concept. Independent means does not depend of the pathway it takes, as long as you start from the same reactants and you end up at the same product. We're going to apply Hesse law in 3 different examples. Example 1, this is reactants going to products. Reactants going to products. This is how your general formula comes about, and this will save you when you are thinking, which formula do I use? You have to be able to get to why the formula works. Otherwise, you will always be, getting one way or the other way correct. Sometimes you get correct, sometimes you get wrong. That is not going to be helpful at all. Why do I start from elements? I start from elements because I'm going to be thinking about formation. So if I form the reactant, this is the formation of the reactant. As you know, forming 1 mole of the substance from its elements, everything at standard states under standard condition. This thing is going to be the formation of the products. Now, if you follow the math and if you can do Hesse's law says that the enthalpy change of this reaction does not depend on this pathway. I can also go a different pathway. I can go this way and then this way. It's the same as going that way. This is the direct pathway. I want to find that I have to go opposite. This way is formation. When I go opposite, it will be minus the formation of reactant. So enthalpy of reaction equal to minus the formation of reactants. Because of my diagram, I am simply following the directions from my diagram, and then I'm going the same way as the formation of products, and that is why it's the formation of products minus the formation of reactants. You might not have seen this formula in this way, but you would definitely have seen it the other way around, which is the formation of product minus the formation of reactants is the exact same thing. I've just rearranged to make the positive in front and the negative at the back there. So you do this in the bracket properly, and you should be able to get to the answer. Okay. Now, just to sum up what we have, we're going to do reactants going to products, but this time we're going to use combustion. When you have combustion, you will have combustion products. We don't know whether it is CO2 or H2 or whatever, but the reactants will give you combustion product. Arrow method, direction methods. Reactants go to combustion product, that is combustion of reactants. And then the products going to combustion products, meaning we are burning 1 mole of the substance in excess oxygen. Everything in standard states under standard conditions. So that is combustion of products. And then we have enthalpy change of reaction there. Now again, Hesse's law says the enthalpy change of a reaction does not depend on which path you take. It could be direct, it could be indirect, as long as we start from the same reactants and are at the same product. Here we are going in the same direction. Here we're going opposite direction, so we have to do minus that thing there. So enthalpy change of reaction equal to combustion of reactants minus the combustion of the product. And that is why this formula works, provided you are not confused between what data are you given. If you're given formation data, it has to be formation product minus formation of reactants. If you have combustion data, it has to be combustion of reactants minus combustion of products. Okay, some people memorize their way through the whole thing, and one day when they make a mistake, especially that one day when it comes to the real exam, and they make that mistake, they mess up every single thing. So make sure you know where things come from, or never forget. Okay, I tend to go for the first route, which is to try and remember where things come from, because I can work out where things come from. Now, the last thing is to do with bond energy. Based on the definition of bond energy just now, what we have is gaseous atoms. But make sure when you have bond energy, when you want to use bond energy in your calculation, this has to be gaseous and gaseous, because the definition of bond energy break 1 mole of the covalent bond into atoms, everything in the gaseous state. Okay, only then we can use bond energy. We are breaking all the covalent bonds into atoms, everything in the gaseous state. It's the same thing with the products there. So this is the bond energy. The bond energy of the reactants is what you need to break. So typically, sometimes they also call this bond energy breaking or bond energy broken. The other thing is, this is bond energy of the products because you are breaking every single covalent bond in the products. And we can be thinking about this in terms of the bond energy formed in this reaction. We want the enthalpy change. Like I said earlier, you can use enthalpy change of formation or combustion to work this out, or you can be using bond energy if everything is in the gaseous state, and which is why enthalpy change of reactions equal to the sum of the bond energy of reactants that you need to break minus the sum of the bond energy of the products that you need to form following the reaction itself. Okay. Now there's one other thing, which is basically experimental chemistry and also physics, which is what is called physical chem, and it's to do with this thing called calorimetry. Calorimetry is to do with Q equal to mc delta T. Now this Q is the heat. This is heat energy. It is not enthalpy. That's why there's no mole associated with it. And whenever you do Q equal to mc delta T, always think about this of the surrounding. So earlier at the very beginning, I focused on surrounding versus systems. This is for the surrounding. This is for the water. So it is for the water, and which is why everything that you have in here must be of the water and not the solid. Do not add in the mass of the solid. Do not add in the mass of solid, whatever solid that you add into the thing, you do not add in the mass, because when you use 4.18 or 4.2, when you measure the temperature change of the solution, you are only thinking about raising the temperature of the solution of the water. You do not raise the temperature of the solid, you raise the temperature of the solution. So the mass of the water is the essential one there. It is only when you want to calculate enthalpy change, so it has a plus or a minus depending on exo or endo reactions. So you need to think about your temperature rising or temperature decreasing. And this is Q of the solution divided by the mole of the limiting reactant. Which one of the reactant get used up? Now this is joule or kilojoule. Usually they will ask you to convert the joule into kilojoule. Sometimes they don't mention, they just say calculate the energy. Then it's a joule, but then they say give the enthalpy change in kilojoule per mole. So you have to remember joule to kilojoule has to be divided by 1,000, and it's something you have to keep in mind our form. And this is in mole. So mole could be, it's not for the H2O anymore because this is the surrounding, this is the reactant, which is the system, but it has to be limiting which one get used up completely. And being enthalpy change, you must have a sign, you must have a value, you must have a unit, and those are typically experimental chemistry essentially. Okay, what I can give you a hint is your practical paper should come out first, if I'm not mistaken, before your theory paper. Usually, if you have this thing in a theory paper, usually they will not come out in practical. Okay, usually if they come out in practical, you won't get much question on this in the theory paper. I say usually because there's no guarantee in anything, because anything and everything in the syllabus could be asked by Cambridge. Okay, I spent about half an hour doing the review of this concept. Typically, these are going a bit slower, but then since you guys have done this topic, many times in AS, so we can just jump straight to question now. So if you got any questions, feel free to raise it up now, and then I'll go through the questions for these chemical energetics, whichever one you want me to go through. Any questions from your side? You can just unmute yourself and then just talk. Yes, Yasmin?
Question 27.
27th. 27th. Okay, so what we have here is the use of Hesse cycle or Hesse's law. It means the enthalpy change of a reaction does not depend on the pathway as long as you start from the same place, end up at the same place. This is the last 10 type of questions, section B. So it has been phased out. You will no longer have a specific 10 questions section B in your new syllabus. You can find out from your Cambridge thing, but it doesn't mean that they cannot ask you 1 question or 2 questions or 11 questions or 12 questions there of this time. So be very careful. Yeah, I'm going to check number 2 first because there's the logic in the series of option. You want T to S. You start from T and then you want to go to S. So I draw an arrow, T to S. I see that I don't have value there. I have value there. So this route is not going to be helpful to me. Perhaps I should go through this way, and then that way. So this is the same direction. So what I do is minus 75. I don't need to add a minus because it's in the same direction. This is going opposite direction. This is plus 92 in this way. When I go opposite, I have to do a minus bracket plus 92. I don't need to do it on my calculator. I can see minus and minus will give me negative. It's going to be exothermic. Endothermic is wrong. Number 2 is wrong. There can only be one answer. Make sense? Okay, next question. I mean, I can show you why number 1 is correct, I guess. If you want, U going to R. If you really want, U going to R. So I get this because number 2 is wrong. There can only be one correct answer. Yeah? But if you want U going to R, you can go similarly. If I go via the green route, so U going to R, I'm going opposite. So it has to be minus and then plus 92. So I'm going opposite way. And then I'm going opposite again. So it's going to be minus bracket minus 134. So minus minus on your calculator will give you a plus, and then you'll get plus 42 kilojoule per mole, which obviously is the correct answer because number 2 is wrong. Only number 1 is correct. So it has to be correct. But without me even checking that and wasting time, I go for the easiest one to check first. And once I get it, the logic, prevails that I get the correct answer straight away. Okay. Any other question, guys? We have about half an hour. Come on. More question is good. I'll try and go through as many as I can. MCQ structure, just unmute yourself and tell me which one you want me to go through. You should ideally have gone through some of these questions before the session, yeah? There's a reason why I posted up the questions a week in advance. I mean, you have your own school revision to go through as well, but these are all AS topic and anything could be asked.
12.
Number 12, did someone say 13 as well? So 12 and 13, am I correct? 12 and 13, okay. Now, in A2, you will have heard of this word spontaneously. This is in A2 energetics, advanced energetics. We know that spontaneous is to do with delta G being lesser than 0, negative. That is when you get a spontaneous reaction. But this is AS. Why in the world do they ask you things like this in AS? Because Cambridge being Cambridge, they like to ask things sometimes which are not really in the syllabus. So be very careful, right? Now, hydrazine does not burn spontaneously. Well, I can tell you number 1 is definitely incorrect because this is a statement. This is a fact. So just because you're liquid, why doesn't it burn spontaneously? Like that doesn't make sense. What else? Despite its use as a rocket fuel, hydrazine does not burn spontaneously in oxygen. I can tell you D is definitely wrong because there's just enthalpy change. Spontaneous means it doesn't happen on its own. It doesn't just happen, It's not like something just burns spontaneously in oxygen because it's flammable. But some stuff are not flammable. They don't burn spontaneously because it's very difficult to happen. Very difficult to make it happen. Okay, so just like when you have graphite to diamond, so you know that, well, you probably don't know that, but graphite is there. If graphite energy level is there, diamond energy level is very similar to graphite, very similar. So, that enthalpy change is very small. The enthalpy change is very small. But why? Why in the world can we not get diamond easily from graphite? So not spontaneous. And the reason is because it looks like that. So what does that tell you? Enthalpy change does not tell you how big the activation energy is. Actually, this reaction is extremely slow and it only happens under intense pressure. You can look up, we can make diamond in the lab by subjecting graphite to intense pressure. And that is what happened in the ground over a long period of time. The pressure underneath the ground, deep down in the Earth's crust, they actually compress the graphite a lot under high pressure. This doesn't happen in the lab without overcoming the activation energy. And this is the very reason why some stuff don't burn spontaneously, because it's to do with rate of reactions, very difficult to overcome this mountain there, this activation energy. So hopefully that makes sense. Someone did ask question 13, right? Did I hear that correctly? Someone wanted me to go through question 13? Yes. Okay, so in this question, you are given equation. So this equation has to be balanced, which it is. And then look at information you're given. Always focus on the information you're given. You're given formation. You're given formation. So some teachers would expect the students to write in the equation, starting from the elements and stuff. What I'm just going to do is I just want to show you what I did earlier. The elements form the substance. The element form the substance. The element form the substance from the element. So that is the formation of the reactant. And then on the right-hand side, you have the formation of the product. And if you know anything about Hesse cycle, you would know that enthalpy change of reaction doesn't depend on the pathway. Instead, I'm going opposite this. So I have to do minus formation of reactant plus the formation of product because this is in the same direction. I can use my formula straight away, which is the sum of the formation of the product minus the formation of the reactant. Be very careful. A lot of students in their entire chemistry journey, they just say product minus reactant. That is a wrong definition. You have to remember it by formation of product minus the formation of the reactant, because when it's combustion, it's the other way around. Now, formation is for 1 mole. Here you're forming 2 mole of the substance. Formation is for forming 1 mole. By right, I should have said the sum of the formation. This thing here refers to sum. It's a Greek symbol called sigma. It means you sum up everything. For forming 2 mole, I need 2 times plus 33 because I am forming 2 mole of the substance. I'm forming 1 mole of the MnO2. So I write down my working and I go very clearly on my calculator, and I'm forming 1 mole of that manganese nitrate, manganese 2 nitrate. I use bracket. So brackets are very important. This is for the product side. So 2 times plus 33 plus 520 negative times 1. I get minus 454 minus and then minus 696. So people say, why should I waste time with my working? Well, if you don't waste time on your working, you risk losing everything later on. If you give this answer in if you give this answer in structured paper, just like your calculator show you, you have lost 1 mark because enthalpy change must have a sign and a value and a unit, and your calculator will not show you when it is positive. So be very careful when you're in a theory paper, when you're in a not multiple choice theory or practical paper. Okay, hopefully that helps there. Next question. Any other questions? More question is good. Can I go through one question with you? I'm going to go through question 14 because of something that I wanted to rest up earlier. So this is quite important in paper 3. So I don't teach A-level anymore, so I really don't know what will come out in your practical, okay? So you can't ask me that. It's not a confidential, it is confidential info, but I wouldn't know anything about it at all. But this is an example of something that I know has come up previously in a practical paper because it's something to do with calorimetry. Calorimetry was basically what I had just shown you earlier. So you put a beaker and then you support the plastic cup or the polystyrene cup on top of it. You have the thermometer in there. What you have there is you put in some HCl, and then you're going to put in the NaOH later on. In a neutralization reaction, so HCl plus NaOH will give you NaCl and H2O. But then you also learned, even from O-level, the ionic equation, H plus A equals plus OH minus A equals, give you H2O liquid. And you have learned this in A2 as part of your KW. So you learn KW is the water dissociation constant. And we know that neutralization is endothermic. So neutralization is, I've got it the other way around. Neutralization is exothermic. It releases heat energy to the surrounding. You are not breaking any bond. Instead, you just have them recombined and you form the OH covalent bond. Not breaking any covalent bond, not breaking anything, just forming bonds, just forming one OH bond. Forming bonds without breaking bond is exothermic. Here, you are just breaking the covalent bond. This is endothermic. Okay, but that is A2KW. We just focus on AS here. Remember earlier when I said Q is equal to MC delta T? The Q there is of the water. So that means all of these is for the water. So here you're not adding solid, it's okay. But students really like to add in the mass of the solid or use mass of the solid for whatever reason, because they don't know about water. You use heat capacity of water. You measure temperature change of water. Why do you use mass of solid? You are raising the temperature of the water, okay? Now what you have in this answer in this question is you mix in the NaOH and the HCl. So what is the total volume of water do I have when I do the reaction? What is the total volume of water do I have? Is Isa there? Hello, hello, Isa. Hello, hello, Isa.
Yes.
Isa, what is the total volume of solution then when the neutralization happens? So you are mixing two things happening, right? What is the total volume of solution?
100.
100. So this is 50 plus 50. So 50 and 50 HCl and 50 NaOH, you get 100 cm3. You should also know that density of water, density is mass over volume. Density of water is 1.00 gram per cm3. When you have 1 cm3 of water, you have 1 gram. When you have 1 gram of water, you have 1 cm3. So 100 cm3 is 100 gram. So your MC delta T, 100 gram or 100 cm3 of water, 4.2 joule per gram per Kelvin. Now this temperature rise by 17 degrees Celsius, and this is the one where here is okay because all of these are 17, but sometimes people, they like to add 273, and that is the biggest danger. The temperature rose by 17 degrees Celsius. If you have Ti and then Tf, so this is temperature, okay, in degrees Celsius. Now I'm going to draw another scale, which is in Kelvin. So this is Ti plus 273, and this is Tf plus 273. And what do you notice? You notice that the temperature change is going to be Tf minus Ti. So even after I add this plus 273, I add this plus 273, temperature change is a difference. Temperature change is not just one temperature. So whether you do it in Kelvin or degrees Celsius, you can see the temperature change in degrees Celsius is the same as the temperature change in Kelvin. So do not add in 273 again to your temperature change because it doesn't make a difference. Even though this is per Kelvin, this is going to be the same as 4.2 joule per gram per degree Celsius because it's delta T. So they are the same. You will also see that this is the same as 4.2 joule per cm cube, joule per cm cube per Kelvin because of this thing here, where 1 gram of water is the same as 1 cm of water. So looking at all this information, we know 50 is definitely wrong because your total mass of solution is not 50. When you do the reaction, the volume of solution that you are heating up is not 50 cm cube, but it's 100 cm cube. And we have the 4.2. We have the temperature change, whether in degrees Celsius or Kelvin is the same. At the bottom, there's the difference then. What we have there is the limiting reactant. You will see that same volume, same concentrations, 1:1. Really doesn't matter which one is which one, but what is important is N equal to CV. Your volume has to be in dm cube because your concentration is in mole per dm cube. So 2.50 must be multiplied by 50 over 1000 or 50 times 10 to the minus 3. So this is in dm cube. This is definitely wrong. So C is correct. So you don't have this A, B, C, D in your paper 3 or in your paper 2. So you got to know how to set up your question properly before you start pressing your calculator. So I hope that helps. Any other questions? Come on, rest it up. We have around 15 minutes. Any other questions?
Structured questions.
Okay. Which question? Or rather, which page number? They don't have question number. Which page number are you looking at? So they got page number at the bottom, right? Which page number are you looking at?
12.
Page 12.
12 to 13.
12 to 13. Okay, first question. This one okay or not okay?
Okay.
These are okay. This one not okay, is it? Okay, with this type of questions, we need to be careful. Here, this is a gas, and obviously oxygen is a gas, carbon dioxide is a gas, and there's a water vapor. Water vapor is not liquid, it's H2O gas. Guess what? Everything is in the gaseous state. Everything in the gaseous state means we can use bond energy. With these type of questions, there's no easy way to go about it. It's built one in, so I'm gonna draw it out. You gotta draw the display formula because you have to break everything. Carbon from 4 bond, that was part of the bonding topic. Carbon from 4 bond, 1, 2, 3, 4. Carbon from 4 bond, 1, 2, 3, 4, so on and so forth. Oxygen, we have 6 of these, so be careful about the stoichiometry. We have 4 of the carbon dioxide, and then we have H2O. We also have 4 of them. So we're going to count them properly. If you count this, you actually have 8 of these energy of OH because there are 8 OH altogether. And similarly, for that, you have 4 times 2, which is 8 CO double bond there. And for the O2, you have 6 of that OO double bonds. And here, this is the one that are a bit tricky. You have 1 time carbon-carbon double bonds there. You have 2 of that carbon-carbon single bonds. And then we have, they don't have a difference between the CH alkene or CH alkane. So we're just going to assume they're all the same. So 1, 2, 3, 4, 5, 6, 7, 8. We have 8 of that CH. A lot of this comes down to bookkeeping. You need to draw and then identify how many are you breaking first. As I mentioned just now, how I gathered the formula, it was the bond energy of the reactants that we need to break minus the bond energy of the products that we need to form. So this is called the sum of the bond energy of the reactants where we need to break, or I say broken, minus the bond energy of the products that I need to form. You will probably have come across this formula at some stage, but you probably didn't know what we did. But I showed you earlier, reactant to products, and then I have gaseous atoms. So this is the bond energy of the product. This is bond energy of the reactant. Hesse cycle says, doesn't matter. Start from a reactant and products. The enthalpy change of the reaction is going to be bond energy of reactants minus, because you're going against that, the bond energy of the product, which is what I'm doing here. So what I'm doing is put a big bracket. I need to break 1 of that carbon-carbon double bond. So 1 of 6, 1, 2. I need to break 2 of that carbon-carbon single bond, 2 times 3, 4, 8. And I need to break 8 of that 4, 1, 2. I also need to break 6 of that oxygen. So 4, 9, 6. Close bracket. Okay, use bracket very well because you don't want to make any mistake with your calculation. So 8 of that CO. And then 8 of that OH as well, so 4, 6, 3. Do not try and press your calculator straight away. Do one whole bracket and then do the other bracket. So this comes down to how well or how fast you can key in your calculator. You will see that I've talked a bit fast, but if I'm not talking, I can work even a lot faster. So by right, you should be thinking in your head and talking to yourself as you are doing this in an exam setting. And you will see that combustion, because we are combusting a hydrocarbon, doesn't matter. Combustion is always exothermic and it always releases heat energy. So I have a sign, I have a value, I have a unit. Very, very important that obviously it's exothermic. Explain that the delta H is lesser than 0 is definitely exothermic there. Okay, I hope that makes sense there. So someone wanted me to go through question 13 as well. This is slightly tricky because this one is not bond energy. Rather, they give you 1, 2, and 3. Why in the world do they give me 1, 2, and 3? They don't specify formation, combustion. Doesn't matter. It doesn't matter. Okay. I look at this first. I'm burning 1 mole of the carbon, and guess what? I can say that is combustion of carbon. But guess what? I can also be thinking about this identity. I talked about identity earlier. This could also be the formation of CO2. I'm forming 1 mole of the substance from its elements. Everything is standard states under standard condition. Similarly, there could be the formation of H2O. When you talk about formation, you look on the product side, form 1 mole of the substance from its elements in their standard states under standard conditions. When I talk about combustions, I look at the reactant side. This is the combustion of hydrogen. Now, how about the first equation there? The first equation here, this is methanol, and this is combustion in oxygen. As I'm not forming 1 mole of a substance, I'm forming 2 different substances. So this is not formation. This is not formation, but what is it? It is the combustion of methanol. Combustion of methanol. So if I only have the combustion data, but I have the formation information, which is identical to the combustion and combustion of that. I should be thinking about combustion, combustion, combustion. And guess what? If I am given combustion data, I should be thinking about my formula, where it is the sum of the combustions of reactants. Why in the world do I remember the formula? Well, I don't really have to. I can go back to my drawing board and get that from basic. But obviously, from time to time, if you already know what you're doing, you should be able to use the formula if you wish. Combustion products. So the arrow is reactant to form combustion product, product to form combustion product. This is called combustion of product. This is called combustion of reactants. You want the enthalpy change of reactions. What do? Well, Hesse law. It says enthalpy change of reaction does not depend on which path you take. So I'm going to take the indirect path. I'm going to go this way. It's going to be a plus. I'm going to go opposite this way. So it's going to be minus the combustion of product. Combustion of reactants minus combustion of products. I'm going the opposite way. Once I've gotten the formula, it's just a matter of putting things into the equation. What do I have? I want the enthalpy change of reaction. Reactant going to products. I have the combustion of these, because I have the combustion of carbons, I have the combustion of hydrogen, I have the combustion of CH3OH. The combustion of oxygen is 0 because of the definition. Oxygen burns in excess. Oxygen does not give you any product, it just gives you oxygen again. Your energy profile diagram will have the exact identical energy level. Enthalpy change of combustion for oxygen gas is 0. So going to the reactant side, remember the combustion is kilojoule per mole. Is for 1 mole of the substance. You have 2 mole of hydrogen. So you need to remember to multiply this by 2 because of the definition. This is for 1 mole of H2. You're burning 2 mole of H2. So I do 1 mole of carbon first, which is 1 time minus 3 times 4. And then I have 2 mole of hydrogen. So 2 times minus 2 for 2. There is nothing for oxygen. That's why they never ever give you. Do not try and use things like bond energy, because I know students are desperate. They just look at the data booklet and they're like, oh yeah, data booklet has a value. Might be nice to use it. But what is the kind of information you're using? Be very careful. Use brackets because we are not to be easily confused. Of course, if you are to be tricked easily, then that become a problem in the real exam. I get from the first bracket minus 578, and then I get from the 7th bracket that one. So as with any mathematical calculations, keep your working tidy. And I will have lost 1 mark because the calculator doesn't show that. Instead, you must remember, have a sign, have a value, have a unit, especially for physical chemistry. So hopefully that makes sense there. Not too sure if this is the question that you wanted me to go through, but I can tell you some stuff. This is P triple P is a hypothetical thing. So this is 2 times P triple P. The P4 is as stated here. How many phosphorus covalent bonds are there? Let me ask, I don't know, Akila, how many phosphorus single bond are there? P4, right? So I need to find out how many bonds I'm breaking, right? Akila, are you there?
Yes.
How many phosphorus covalent bond do I have? P4.
4.
You see, I knew that because this is the very reason why this kind of question are given. Let's count 1, 2, 3, 4, 5, 6. The diagram is given. There are 6 times phosphorus single bond. Count it. This is what they have shown you. Okay, 6 of that. And if this is multiple choice question, it could be, one of the answers will be 4 times that. If this is structured question, you will have lost 1 mark because you have gotten that one wrong. But of course, once you've gotten the value, it should be quite easy. 2 times that minus 6 times 198, and you should get the enthalpy change of reaction. Okay. Any other questions? Oh, actually, before we finish, can we all just turn on our video? Let's just take a quick photo, and then we can continue with the questions. Let's just turn on our video and take a quick photo for attendance. So 1 hour is pretty short, yeah? So you need to really, I don't know, I mean, as exam is happening. Are you there, Shakira? just start taking the first photo first. We're waiting for Shakira. Smile, you're on camera. 1, 2, 3. Let's take another one. 1, 2, 3. All right, all good. Okay, we can just turn off our camera now. But yeah, okay. So next week will be 2 topics combined into one, because redox reactions is quite short. Redox is quite short, so I can combine the 2 into one. As far as I know, AS is happening in May, maybe, for paper 2. So I don't know. Do you guys want me to go through a past paper, or do you want me to continue the topic by topic? I'm open for discussion. I mean, it is what you want. What do people want me to do next week? Do you want me to go through some past year papers, or do you want me to, you know, go through topic by topic still? So we still have quite a lot of topics to go through actually. What are people's opinions? Any thoughts? Any ideas?
Topics by topics.
Okay.
Okay,
topic by topic is good, but I also know a lot of people struggle with organic. The next big chunk, we still have equilibria, which is calculations, and periodicity, which is all of that inorganic chemistry, like group 2, group 7, and then trans and nitrogen and sulfur. And the last one is obviously organic chem, which is everything. So any particular preference, which topic you want me to go through first? Or you want some time to think about it? Well, I'll give you time to think about it. I'll put out a comment section in the Google Classroom, and then you let me know, and I'll take into consideration what you feel, which topics are the most worth it to go through. When I say organic, organic can be broken down into 2 chunks. Yeah, the first organic section will be like the isomerism, the alkane, the alkenes, and and alcohols. Okay, and then the next chunk will be all that carbonyls, mass spec, infrared, carboxylic acid, esters, halogenol alkane. So those, because organic cannot be done, you know, like one. It's better to be done like as a chunk, but I'm open for, you know, suggestions. So do leave the comments to think about it, and we'll consider what is the best thing to do starting next week onwards. Okay. Any other questions in this calorimetry and energetics kind of topic? I mean, there were a few formulas, but you know, there is no use if you forget the formula if you don't know where they come from. I have tried to show you, you know, where things come from, so that you will never ever forget if you know how to work out where things come from. Any other questions in here you want me to go through? We still have around 1 minute. I can be very fast. Anything in here that are still confusing to you? Nope. Okay. So I guess, okay, well, if you got any questions, just ask on the, you know, Google Classroom. I'll be more than happy to reply you there. Session is recorded. You can catch more of the topical playlists. So actually all the topical playlists are available on my channel already. Like, you don't have to wait for this kind of topical session before you go through the topical playlist. If you don't know where to find the links, just let me know. Yeah, so even though I put up the materials for next week to be rate of reaction and redox, we don't necessarily have to go through those. We can go through organic or inorganic chemistry or equilibrium or anything. Okay, but you got to let me know in advance. I'll put out the comment section later on, immediately after this. So do comment away so that I can put out some materials in advance, so that you can review those materials rather than just thinking about what question you want to ask on the day itself. Is pretty bad because it doesn't help you that much. Okay, I'll stop it here for today. So have a good day, guys. And yep, so do comment away on Google Classroom later on, yeah? All right, so have a good day. Thank you.
Thank you, sir.
Thank you, sir.
Okay, bye-bye.